A very good morning to one and all. I, Dr. G. Haripriya, HOD of Department of H&S and convener of 1 week international online FDP program entitled Mathematics for a Better World. I'm happy to introduce our resource person of today's session on mathematical modeling, fluid aspects of biological systems, Dr. Krishnamacharya, Professor of Mathematics, IIT Kurnool, who has a very good track record of teaching experience. Sir has completed his graduation and later pursued MSc from SV University, Tirupati. He obtained PhD from reputed IIT Kharagpur. He has rich teaching experience of 41 years and worked in various colleges. He has worked at NIT Warangal for 34 years, also worked at the University of Calabar, Nigeria in the year 1980 to 1982. His research experience include biofluid mechanics, heat and mass transfer. He worked on 80 papers in both national and international journals. Sir has efficiently guided many projects and PhD students in the field of mathematics. Sir has completed research projects in studies in biomechanics and studies in biofluid dynamics. His administrative experiences as editor, Rencol Times at REC Warangal for about 5 years from 1992 to 1997, member conveners team for MSET 1990 at REC Warangal, as a member UG admission committee at REC Warangal during 1993 to 1994, member PG admission committee at REC Warangal during 1999 to 2003, co-convener ESET 94, co-convener ESET and co-convener MSET Engineering Re-Examination 1996, head of the Department of Mathematics and Humanities during 1992 to 2002, Chief Warden of REC Hostels during 2001, Chief Warden of REC Hostels during 2001 to 2003, Register of NIT Warangal during January 2004 to October 2005, Dean of Academics, NIT Warangal during April 2011 to June 2011, Dean of Students Affairs, NIT Warangal during July 2010 to June 2012, Member Board of Governors, NIT Warangal during December 2013 to November 2015, Professor in charge Legal Cell, NIT Warangal during December 2012 to July 2015, President ISTAM for the year 2021. He won many accolades and distinctions like cash prize for obtaining highest percentage in all PG programs of SV University, Tirupati, author of course material for mathematics at B.R. Ambedkar Open University, Hyderabad, expert committee member of MSET, and so on. Presently, Sir is working as Professor of Mathematics at IIT OM since June 2020. Sir, we are very fortunate to have you for today's session, and I request you to address the participant. Sir, please take over the session, sir.
Yeah, very good morning to all of you. At the outset, I would like to thank the organizers of this program, the management of this Institute, Gates Institute of Technology, Gutti, and in particular, Dr. Haripriya, the head of the Department of Sciences and Humanities, for giving me an opportunity to interact with all of you, share some of my views with all of you today morning. I am told that this is a faculty development program where faculty are drawn from different institutes, colleges, from the departments of mathematics and computer science also. And the topic I have chosen, of course, already Dr. Haripriya mentioned, is mathematical modeling, applications of the concepts of fluid mechanics to biological systems. But then because there are faculty from different disciplines, first I will speak about the fascinating world of mathematics for some time, maybe about 20-25 minutes. Then I will give 2-3 very interesting mathematical models, case studies. One is related to computer science, which is in Markov chains. Other one is, presently, of course, we seem to have come to the end of the COVID pandemic. Of course, we don't know exactly. We had been through a very tough time during the last 2 years. And in this context, the mathematical aspects of epidemiology have received a lot of attention. I am sure all of you would have followed, Sutra model. Often it is reported, some professors from IIT Kanpur, IIT Hyderabad, they constructed a model and so on. In this context, I would present a model which shows how mathematics, in particular differential equations, can throw some light on the, the growth development of this pandemic. When does it reach peak? When does it fade out? What are the parameters which govern? Of course, the model which I am going to present is a very elementary model, very crude model, but that shows the potentiality of mathematics in different contexts, including epidemiology, which is the present problem, right? Then, of course, I'll also present one model related to eigenvalues, eigenvectors, then systems of differential equations and so on, small, simple models. Later, I'll go to the main topic, namely mathematical modeling and, the applications of fluid mechanics to biological systems. Very fascinating topic, which deals with the fluid mechanical aspects of blood flows. Then, some other systems in the human body. I'll try to throw some light on the physiological aspects, then the fluid mechanical aspects. How does fluid mechanics help us to understand the biological systems, and in what way it helps biology, and in what way biology helps engineering, or for example, for that matter, mathematics. It is a two-way cooperation. It is not that mathematics only helps biology. Biology also helps technology. Biology helps mathematics and so on. So this is how I plan to present my topic. First, let me talk something about the fascinating world of mathematics. Mathematics, normally people think, is a branch of science. Mathematics is not merely a branch of science. Mathematics is a way of thinking. To be mathematical means to be rational, to be logical, to be precise. You follow? That's why you see most of these examinations, banking examination, railway recruitment, UPSC preliminary examination, all of them contain mathematical questions. Time and distance, time and work, all these things. Because the basic understanding is, if somebody is good at mathematics, he will be good at logic, and thereby he will be good at any situation which needs analysis. That is the reason why all these competitive exams, including IIMs, all these aptitude tests, they all involve only mathematics. UPSC preliminary, recently one of our medical officers, she appeared. She took help from me because she could not understand the problems. Preliminary UPSC prelims, not the mains, of course. So all these things go to show mathematics is not merely a branch of science. It is a way of thinking. It is a philosophy. It is a universal language. It is the language of nature. It is not my words. It is the words of famous scientist Galileo. Galileo said, if you want to understand, analyze the universe, the nature, the language you need is the language of mathematics. And in this language, the alphabets are straight lines, triangles, circles, ellipses, parabolas, hyperbolas, and so on. Without the use of these concepts, these alphabets and mathematics, you can never understand nature. And if you make an attempt without using mathematics, you will be wandering in darkness. This is what he told about mathematics being the language of nature. Okay, there are many beautiful examples. I will not go into all those details. One simple example is Fibonacci sequence. I think most of you must be knowing Fibonacci sequence, a problem which was posed way back in hundreds of years ago, maybe 12th century, something like that. And that problem posed by somebody, very innocent looking problem, very simple looking problem, that gave rise to so many concepts today. Even today, there is a journal, Quarterly Journal of Fibonacci Sequence. It is useful in so many things. It has got so much of relevance in nature, because the arrangements of leaves on the branches of trees, the arrangements of petals on the flowers, the arrangements of seeds in many vegetables, fruits, they all follow Fibonacci sequence. It has got so much of relevance. Similarly, the concept of golden ratio, divine ratio, I'm sure all of you would have heard. That is one mathematical number which has been studied extensively over centuries by not only mathematicians, by construction engineers, by architects, by painters, by sculptors, and so on. One simple number which has been studied by so many people belonging to so many disciplines. The reason being that particular number is used in the construction of so many ancient structures like palaces, temples, churches, mosques, and even pyramids. The reason being, it seems if a construction is made where this divine number, divine ratio is used in some context or other, it appeals to the human eye. In human eye, there is a rod-like structure. So when a construction is made according to this divine ratio, it pleases the human eye, and human being appreciates the aestheticity of that particular structure. That is the reason why, and it is a mathematical number, some 1.61, something like that. There is a relation between divine ratio and Fibonacci and so on. I will not go into the details of all those things, okay? And I said it is a language of nature. And mathematics is a language of science and technology. Mathematics is the language of science and technology. It is the heart and soul of science and technology. Okay? But for the abstract and consistent findings of mathematics, many important discoveries would have eluded humanity. Name any important discovery, any important invention in any branch of science, in any branch of technology, any discipline of technology. Invariably, mathematics would have been the basis for all those discoveries, for all those inventions. Mathematics permeates all branches of science, all disciplines of engineering, all walks of life, all spheres of activity. In mathematics, every equation has a history, every result has a story, every equation has a beauty, and every concept has an application. Another beautiful thing about mathematics is mathematics, there is no redundancy. All of you, all of us we are all students of mathematics. We see mathematics theorems, hypothesis is given. There is no word, no sentence which is redundant in the theorem. If you are not using which is given in the statement, that means the theorem is ill-posed. For example, you take Cauchy's theorem, Cauchy residue theorem. So FZ is analytic, so and so, so and so. Every word you use there, we use it in the course of proving that particular theorem. If something is not being used, that is redundancy. So mathematics, there is no redundancy. Okay, and to illustrate the importance of mathematics, I will give an interesting anecdote involving Albert Einstein. We all know Albert Einstein is considered as one of the greatest scientists of all times. Albert Einstein, during the college days, he was always obsessed with physics. He used to think of physics all the time. And in the process, he used to skip classes of other subjects. He used to tell one of his friends, my dear friend, I want to think about physics because I am interested. I am obsessed with physics. So please write down the notes for me. I will copy it from you later and I will study. So his friend used to write the notes neatly. Einstein used to copy it, and of course, he passed with flying colors. Later, he went on to become a scientist. When he was working on a problem, his intuition told him this is going to be a path-breaking result. This is going to be a revolutionary result, a path-breaking result. But the mathematics which he got became very, very clumsy, very, very haphazard. In mathematics, you know, when we are asked to solve a problem, if we commit a mistake, we ourselves would realize something has gone wrong. Suppose the problem is given. Find the value of x square plus y square plus z square equal to. Normally, the values will be 0, 1, 2, something which is, there is some sort of pattern. Suppose you are getting 191 by 367, something like that. We ourselves would realize something seems to have gone wrong in the calculations. So Einstein thought, since the equations are becoming very clumsy, some concept needs to be used here. Some concept, he did not know what is to be done. He asked his friends, his teacher, they said, we don't know anything. He went and asked his old college mate, my dear friend, I am working on a problem and my intuition tells me it is going to be a path-breaking result, but the mathematics I got turned out to be very, very haphazard, very awkward looking. I think I need to use some concept. Can you please look into this and tell me? Then his friend had a glance at a particular, mathematical part. Then he said, you fellow Einstein, when you were in college, you did not, you skipped many classes of mathematics. In mathematics, we study one concept called a tensor. I'm sure mathematics students are aware of this tensor. And we represent a tensor using matrix, a very familiar concept. I think if you use these things, possibly you will get over your difficulty. Then Einstein studied tensors, studied, of course, how to represent them using matrices for a few months. He applied them. Then he got all those clumsy looking, awkward looking, haphazard looking mathematical equations got reduced to a single, elegant, beautiful equation, and that resulted in the theory of relativity. We all know theory of relativity is a very phenomenal, path-breaking, revolutionary result. Then Einstein tapped his head and said, unnecessarily, I missed the class of mathematics. Had I attended those class of mathematics, I would have given this theory of relativity 3 years earlier. So the moral of the story is, every concept we study in mathematics will have applications somewhere or other. I may not know the application today. The mankind may not know the application today. You may not need a particular concept in your particular situation, but every properly coined, properly formulated mathematical concept will have invariably applications somewhere or other. And Swami Vivekananda, somebody asked Swami, you said God is everywhere. If God is everywhere, why do you construct so many temples? Then what Swamiji said? Swami said, you see, air is everywhere. Air is everywhere, but why do you need fans then? You see, we are telling air is everywhere throughout the universe. Then why do you put a fan? You see, air is there, but you need a fan to drive the air. You follow? So is the case with mathematics. We have so many engineering branches: civil engineering, electrical engineering, mechanical, ECE, computer science, biotechnology, chemical, so forth. But for all these branches, mathematics is the driving force. Their concepts are there, but you need mathematics to make them implementable, to make them application oriented. So mathematics is the driving force for all the engineering subjects. That's why I said it is the heart and soul of science and technology. In fact, Dirac, a famous mathematician, somebody asked him how to explain the beauty of mathematics to somebody. Then Dirac said, the person who asked that question is a mathematician. You need not explain to him about the beauty of mathematics. But if the questioner is not a mathematician, you can never explain to him. You follow? If somebody is a mathematician, naturally he would understand. If he is not a mathematician, he can never understand. You follow? It is said mathematics is music for the mind. When you go to a musical concert, people who understand the subtleties of music, the raga, the thala, and so on, they simply cannot keep quiet. They keep doing that, they swing their body, they swing their head, and so on. So music swings the body, but mathematics swings the mind. The mind, vibrates, swings when you read mathematics, implement mathematics, or teach mathematics, or study mathematics. That is the beauty of mathematics. I will not go into the details of applications. I will mention only 2-3 examples. If normally mathematics, many concepts are given out of intellectual curiosity by eminent mathematicians, but the applications are known much later. Just because a concept may not find applications today doesn't mean it will not have applications. Okay? For example, you take conic sections. We study parabola, ellipse, hyperbola at the +2 level, I believe. Okay? Conic sections was given by Grecian mathematicians 2000 years ago. They were very fond of mathematics. You follow? And they used to think even God is a man of geometry. God geometrizes forever, they used to say. And they used to put a plaque on their door. If you don't know geometry, please don't enter my room. So they used to think that geometry is so important. If somebody does not know geometry, he is fit for nothing. So such was their fascination, admiration, understanding of geometry. And what is a conic section? It is a plane curve traced out by a particle which moves so that the ratio of a distance from a fixed point, which we call focus, to its distance from a fixed line, which we call directrix, bears a constant ratio. That ratio we call it eccentricity, equal to 1, less than 1, greater than 1, ellipse, parabola, hyperbola, all those things we say. Okay? Using this definition of conic section and the Aristotelian logic, they systematically derived all the formulae related to conic sections. The formulae which we study in the books today, which we teach today at +2 level, most of them have been derived by those Grecian mathematicians. 16 centuries later, Kepler, German astronomer, after a painstaking study of the sky, came up with 3 laws of planetary motion. One law says every planet traverses an elliptic object with the sun at the focus. He used the formula given by Grecian mathematicians. Few decades later, British mathematician physicist Newton, he derived this as a particular case of all-encompassing universal law of gravitation. And in this today, it is the satellite age. The importance of the formulae of conic sections in the context of satellites need not be overemphasized, because we know path of projectile is a parabola. We sent, even India, we sent a satellite to the moon. You follow? There, whoever sends it, in the course of the travel, in the course of this orbiting everywhere, the formulae related to conic sections are needed. A mathematician may not go and sit in the satellite center, but the formulae, the concepts given by mathematics and mathematicians are being used by the satellite scientists. And conic sections are needed for determining the positions of planets, for predicting eclipses. You see our astrologers, our purohits, they tell when the eclipse comes, they don't know anything about astronomy, but still they do it. It is all mathematics only. It is all the concept of conic sections. And another thing is, beautiful thing is, we all travel by cars, automobiles. Automobile, there is a headlight. The headlight in the automobile is the application of the mathematical concept of parabola. And today, we all talk of energy crisis. What is the solution for that? As Dr. Abdul Kalam always used to say, the solution to the energy crisis is the solar power. Solar power is freely available, everywhere available. Ours being a tropical country, we have more access to the solar energy. What we do in the case of solar energy, we put panels on the rooftop. The panels absorb solar energy, and then we try to harness it, convert to some other energy we need. And now people realize, people are working in IIT Madras, instead of a straight panel, if you put a parabolic panel, there will be more focus of solar energy at the focus, right? At the focus. So they try to extract it, harness it, and get more energy. So you see, the concepts given 2000 years ago, whether they knew about their applications or not, we don't know. But today they are being used in so many different contexts. One more example is simple example, binary system. I think binary system is studied or taught in the 7th class or 8th class. Is it right? What is that? Normally we represent number using 0 to 9. Somebody thought, why not we represent using zeros and ones? Who did it? Let us not bother. Maybe it is a Indian say we have done it, others say we have done it. Let us not bother. So I think we all know, if you want to represent a number 125 using binary system, it is a long string of characters, zeros, 1, 1, 0, 0, 1, so on, so on. It is a tortuously long string of zeros and ones characters. Nobody ever imagined it will have applications. But today it is a computer age. And in the computer, whatever language you use, whatever platform you use, computer, the circuit uses only one thing. Circuit is on, circuit is off. On means 1, off means 0. So ultimately it is a binary system which helps us to interact with the computer. So what was started as a possibly a out of intellectual curiosity turned out to be a boom for mankind. Today, can we imagine life without computer? I'm talking to you, computer. I'm talking to my daughter who is in USA, computer. Everything is because of computer only ultimately. Okay. And one more simple example I'll give. I think all of our students are mathematics. In mathematics, Newton gave the was trying to study the motion of particle using what are called fluxions. All that he wanted was, suppose a particle starts here with a particular velocity, after some time where it will be, or if it is at some other place so and so, how much of distance it has traveled, some such related questions. When he completed the study, he realized not only he understood the concept of motion of particle, but he came up with what is known as calculus, rather the concept of limit. The concept of limit is considered as the greatest creation of human mind, because without limit there is no continuity. Without limit there is no differentiability. Without limit there is no integrability. Without limit there is no convergence. Without continuity, without differentiability, without differential equation, without integrability, without convergence, can we imagine any branch of science? Any branch of science or any discipline of engineering, because in every branch of engineering, we are concerned with rate of change of displacement, rate of change of velocity, rate of change of linear momentum, rate of change of angular momentum, rate of change of entropy, rate of change of profit, rate of change of population, rate of change of epidemics today, epidemiology. Wherever rate of change is there, derivative comes into picture. We know the physical application of derivative is rate of change. Okay. So without limit, there is no continuity. There is no differentiability. There is no differential equation. What do we study in engineering then? So what Newton, while trying to study innocently the motion of a particle, discovered calculus, which today turned out to be a boon for the mankind. That's why, as I said, calculus is considered as the greatest creation of human mind. Okay, these are some of the examples I want to set. I think there are many other examples, like, you know, computer science people, they may be knowing, or ECE people may be knowing. We discuss what are called wavelets. I think we all study Fourier series. Your Fourier series is a beautiful subject given by Joseph Fourier. You know, while study the heat conduction in a metallic bar, came up with the Fourier series. And today, you use Fourier series for signal processing, for communication theory. And the Fourier series of inadequacies, it led to lots of developments like discrete Fourier transform, fast Fourier transform, and so on. Ultimately, today we have what are called wavelets. I don't know how many of you know wavelets. Wavelets are extensively used in electronics and communication engineering, in fluid mechanics, biomedical technology. And for all that wavelets, the mathematics that is needed is functional analysis. In mathematics, we study functional analysis. We think it is a pure mathematics subject. It doesn't have any applications. It is only fancy tie of a mathematician. That is what people used to think. But today, it is a functional analysis which is a prerequisite to understand and develop wavelets, which are extensively used in communication engineering, in geophysics, oil exploration, exploration of minerals, and in fluid dynamics, aerodynamics, wavelets. And definitely, we all use mobiles today. There is nobody who doesn't have a mobile. And we are able to communicate to anybody in the world using mobile. How? It has got an antenna. And antenna is designed using a mathematical concept called a fractal, F-R-A-C-T-A-L, fractal. Very roughly speaking, it is a fractional dimensional entity, or it is a infinitely divisible self-similar entity. You know, I will not go into the details of that, but again, you need so many concepts of topology and function analysis to understand this concept of fractal. And you know, in the mathematics students, we all study Cantor set in real analysis. It is the origin for the development of this fractal geometry. Fractal geometry was developed by Mandelbrot, and it is a generalization of classical geometry. Why? Many things in nature are not regular. For example, the top of a mountain is not regular. The edge of a cloud is not regular. The feather of a bird is not regular. The continent, for example, India map, if you take, the coastal line is not regular. How do we measure them? In order to do that, this particular fractal geometry is developed. You know, the Star Trek movies, the cartoon movies, they all use this. So here, the basic concept is, normally you say 1 dimension, 2 dimension, 3 dimension, or 4th dimension, time, and so on. Here we talk of what is called fractional dimension, 0.62 dimension. You may think, what is this meaningless? How can there be 0.62 dimension? You see, when we start thinking out of box, unconventional way, it leads to wonders. That is how the fractals are born. Today, fractals play such an important role in biomedical technology, especially, you know, in deciphering so many things. Signal processing, in fact, NIT Warangal, EC department, many people are working on that. I was a member of the doctoral scrutiny committee for them. So they took fractal paper and I conducted examination for them. That shows the importance of mathematics in divergent subject. Why artificial intelligence today we talk? I am teaching artificial intelligence students in AAADM Kurnool. You know, artificial intelligence, what are the basic things you need? You need linear algebra, you need probability and statistics, and you need elementary computer programming. Then you develop. And today, can you think of any speed of activity without artificial intelligence? You go to bank, you only need one. That app is developed using artificial intelligence everywhere, including COVID, Amazon, Flipkart, everywhere they use only the so-called artificial intelligence. And for that, the basic prerequisites are mathematics only. Anyway, I will not go much into the details of that. Now I will present 2-3 simple models, okay, illustrating the importance of mathematics in the with reference to computer science. One is Markov chains, another is diffusion process, third one is epidemiology. After that, I will go to fluid dynamics. Now let me share. Yeah, can you see the screen? Hello?
Yes, sir. Yes, sir.
Yeah. Okay. Yeah, I think I'll skip this one. This I will skip. This is mathematical modeling. What is that we do in the case of mathematical modeling? So we try to, first understand the problem, then construct a model, then use a mathematical technique. Then we try to, I think I'll go to this one. Analysis, adequate model. Yeah, you see how to use mathematics. Real world problem you have, you idealize, do some approximations, then construct a real model, then abstraction and a symbolic representation, then you get a mathematical model, then you go to mathematical theory or technique, then conclusions, and compare with the real world. That is what we call validation. When we construct a mathematical model, we need to validate it, whether it's correct or not. If it doesn't do it, again, you go back and do some other approximation, right? For example, sometimes, when the problem is too complicated, we cannot study all the aspects. We suppress certain aspects and take only one particular characteristic aspect which we want to study. We do some approximation, some idealization. Then if it is creating some problem, we go back again to iteration. Computer programming, we do, these loops, you put in loops. So you do loop, again you do loop. So you go back and then try to improve that one. And now this is Markov chains. Yeah, this is a simple example, beautiful example. 1 minute. I don't know how to. Yeah, anyway, consider a system that is at any one time in one and only one of a fixed number of states. For example, whether in a certain area is either rainy or dry. Okay, if you take the weather here, today either rainy or dry. A person either a smoker or non-smoker, who either go or do not go to college, who live in urban, suburban, rural area, and so, or who buy some car. As time goes on, the system may move from one state to another. We assume that the state of system is observed at fixed intervals and so on. In many applications, we know the present state of system and wish to predict the state at the next observation period or at some other future observation period. You see, we often can predict the probability of the system being in a particular state at a future observation period from its past history. This is very important, especially in stock markets and in business, actually, marketing, all where these particular things are used. Yeah, a Markov chain is a process. A Markov process in which the probability of system being in a particular state at a given observation period depends upon only on its state at the immediately preceding observation period. 1 minute, this is disturbing me a bit. Yeah. Suppose the system has n possible states. For each I is equal to 1 to n, j equal to 1 n, let a TA be the probability that the system is in a state j at a certain observation period. It will be in a state I at the next observation period. TAJ is called the transition probability. I hope you can understand. I am sure the computer science faculty, I'm sure they must be very familiar. System has n possible states. For each I equal to 1 to n, j equal to 1 to n, Tij the probability the system is in a state j at a certain observation period. It will be in a state I at the next observation period. T is called transition probability. Suppose TA is a, since Tij is the probability, we know probability is a real number which belongs to the closed interval 0, 1. So 0 less than or equal to Tij less than or equal to 1, 1 less than or equal to I, j less than or equal to so n. So and so, so and so. Since this is the system is in a state j certain observation period, it must be in one of the n states at the next observation period. So you see here T1j plus T2j plus Tnj. Okay, at the observation period, it is in j. Next state, it may be 1, it may be 2, it may be n. So total probability is 1. That is what we say axiom of probability. The probability of the universal space is 1. It is convenient to arrange the transition probabilities in the n by n matrix, which is called transition matrix and so. Okay. Now we take an example. A weather in a certain city is either dry or rainy. As a result of extensive record keeping, it has been determined probability of rainy day following a dry day is 1 by 3. Probability of rainy day following rainy day is 1 by 2. You see here this probability of rainy day following a dry day. This is rainy day. You see here 1 by 3. Rainy day from dry day it is becoming rainy day. That is 1 by 3. Rainy day to rainy day it is 1 by 2. So D means dry day, R means rainy day. Then the transition matrix of this Markov chain is dry to dry, dry to rain, rainy to dry, rainy to rain. Okay. Similarly, another beautiful example: a market research organization is studying a large group of coffee buyers who buy a can of coffee each week. It is found 50% of those presently using brand A will again buy brand A next week. 25% will switch to brand B. 25% will switch to another brand. You see here, A, you take first column, then you see the side A. A to A, it is 50%. 50% will continue with the brand A. A to B, 25% will switch to from A to B. 25% will switch from A to D. Similarly, B to B, it is 30%. B to A, 60%, and so on. So this is what is called the transition matrix. Okay. So this is a concept which is very useful in marketing, you know, because marketing, people need to know what is the present trend. Otherwise, they will lose everything. In the market, they will lose. Yeah. Now I shall use transition matrix, the Markov process, to determine probability of system being in any one of the n so and so. Xk denote the state vector of the Markov process at the observation period k, where Pjk is the probability system is in a state j at the observation period k. So P1k, P2k, and so. Following theorem. It's a beautiful theorem. We will not discuss about that. If T is the transition matrix of a Markov process, then the state vector xk plus 1 at the k plus 1 the observation period can be determined from the state vector xk at the kth observation period. Xk plus 1 is equal to T into xk. So x1 is equal to T into x0. X2 is equal to T into x1. That is T of T into x0, T square x0. So you see, beautiful theorem. Once you know the state vector, initial state vector, and the transition matrix, you can get the state vector at any subsequent observation period. So this is the beauty of mathematics. This is just like our eigenvalue problem. You see, A is equal to lambda into X, so and so. Now example, the first example. To begin with, let us say it is a dry day. So D dry is 1, rain is 0. Then the state vector 1, the day after we begin observation is X1 is equal to T into X0. The T we have calculated that 2 by 3, 1 by 3 and so on, so on. So T into X0, it gives X1. X2, T into X1. So you see beautifully, you see, slowly it is becoming convergent. See how many things are involved here, you see. We are using matrix. We are using eigenvalues. We are using convergence. You see here, X2, X3, X4, X5, slowly it is, that's why I said, what is convergence? We all know convergence depends upon the concept of limit. Without limit, you can't talk of convergence. Okay. So on the fourth day, the state vector is always the same. That means from the fourth day on, it rains about 40% of the time. Similarly, second example, survey, that market example. Anyway, I will go through these things so and so. As n increases, state vectors approach the fixed vector. That means longer run, brand A will command 15% of the market, brand B will retain 27%, other brands will command about 22%. You see the beauty. Using simple mathematical model, we get a rough idea what is going to be the market for the brand A. You see, if they get an idea, accordingly they can prepare, accordingly they can market. If they think everybody will buy my brand, they will prepare so much of copy and dump it in the market. Ultimately, it will get spoiled and they will incur losses. So you need to have an idea about the marketing. Accordingly, you will manufacture and so on. So the simple mathematical concept gives so much of interesting results. Then I think I will skip it. Then these are all theory part. I think I will skip these things. Okay. Then this is a very simple example, but involving so many mathematical concepts. You see, there are two cells, cell 1, cell 2. Okay. Two adjoining separated by a permeable membrane. Suppose the fluid flows from the first cell to a second one at a rate that is numerically equal to 3 times the volume of the fluid in the first cell. You see, amount of fluid present in the cell 1 is X1. Amount of fluid flowing through cell 1 to cell 2 is 3X1T. You see, numerically equal to 3 times the volume of fluid in the first cell. Then it flows out of the second cell at a rate that is numerically equal to twice the volume in the second cell. You see, this is from cell 2, what is going out is 2X2T. It is twice the volume that is present in the second cell. X1, X2, we are calling the fluid. Yeah, now, you see, we are converting them to equation. Change in volume of the fluid in each cell is the difference between the amount flowing in and the amount flowing in. Since no fluid flows into the first cell, dx1 by dt, the rate at which the amount in the first cell changes, it is only outflow, there is no inflow. Since it decreases minus 3 times x1t. Minus it indicates fluid is flowing out of the cell, 3x1t so and so. And for the second cell, this minus 3x1t, it is a loss for the first cell, it is a gain for the second cell. So it is a positive one, and from that outflow is 2x2t. So dx1 by dt is equal to minus 3x1t, dx2 by dt is equal to 3x1t minus 2xt. We have got two first order linear differential equations and it is coupled. How do we solve it now? You see, this is the beauty. We are putting it in the matrix form. This is the derivative. dx1 by t, dx2 by t. I am calling x1 prime, x2 prime, a into x. So x prime is equal to a into x. This is something like our eigenvalue problem. You see, eigenvalues of the matrix minus 3, 0. We are getting eigenvalues and the corresponding eigenvectors. Then xt is equal to x1t, x2t, constant of proposed, this is constant, integration constant, plus this eigenvalue 1 minus 3 e power minus 3 corresponding eigenvector, this is second eigenvector. So the solution is a linear combination of these two linearly independent solutions. If we use initial conditions, we get the solution. So you see a simple problem, diffusion from two cells, which we find everywhere in industries, in biology, and so on. We have used matrix theory here. We have used linear algebra. We have used differential equations. We have used systems. We have used eigenvalue problem. We have used initial conditions, and we got finally solution. So many concepts are used. I am sure those who teach MSc mathematics, we use this particular concept, you know. There's a beautiful book by Martin Brown. Anyway, now I discuss this particular epidemiology. Epidemiology, I was telling you about, you see, this quotation you see, Harold Varmus, Nobel laureate medicine 1989, former director National Institute of USA. Scientists can wage an effective war on disease only if we as a nation and a scientific community harness the energies of many disciplines, not just biology and medicine. The allies must include mathematicians, physicists, engineers, and computer and behavior scientists. I made this case repeated during my tenure as director of NIH. You see, this statement was made by Nobel laureate way back in 1989. That is around 33 years ago. Today, we are in the COVID pandemic, and we realize that in order to understand the development, the behavior of this COVID coronavirus, we need not just medical people, not just biology people, but mathematicians, physics, engineers, computer behavior scientists. So this Harold Varmus, Nobel laureate, told this 33 years ago, and today it is becoming a harsh reality. Yeah. Now epidemiology, I think I will not give into this. Acute, chronic, all these things I will skip. Mathematics, what are mathematical model? Yeah, simple model. You see, a simple deterministic model. In a given population at time t, let S be the number of susceptibles, number of those who can be infected. IT be the number of infected persons in the population. RT be the number of those removed in the population by recovery, immunization, death, hospital, by other means. NT is the total population size. ST, number of susceptibles. IT, number of infected. RT, number of people who have been removed. Total is a constant. So you take a population today, to begin with 2020 February, for example, the number of corona cases were 0 in India. Somebody arrived from abroad, one infected person, then he came and infected, slowly he started. So susceptibles, infected people, removals. After that, what you do? You find somebody is now not feeling well. You do test. Then you find he or she has got corona. Remove him and put in the isolation. So this is the removal. Okay. So total is n number of population constant. We consider a simple epidemic model in which there are no removals. As I told you in mathematics, to begin with, we use some approximation, idealization. So this RT we are removing. So ST plus IT is equal to n plus 1. To begin with, n people are there. One infected person has come. ST plus IT is equal to n plus 1. S naught, susceptibles are n. I naught, infected person is 1. So the population, for example, Indian population, let us say 130 crores. One fellow has come from outside. So this S is, n is small, n is 130 crores. I0, I naught is one fellow who has come from outside. Now who is spreading. Due to infection, number of susceptible decreases, number of infected persons increases. Okay. So population is there. For example, you take Hyderabad population, say some 80, 90 lakh crores are there. To begin with, there is no infected person there. Somebody has come from outside. So number of susceptibles now, as the people get infected, number of susceptible decreases, infected persons increase. So you see, ds by dt is minus because it is decreasing. Di by dt, it is positive because it is increasing. So here we assume rate of decrease of ST, rate of increase of IT is proportional product to the number of susceptibles. So it is a law here. ds by dt is proportional to S into I. S is susceptible, I is infected. So this is negative, this is positive. Then of course I will not go into the mathematics. Then you solve it. And finally you see here, limit st as t tends to infinity, it is 0. You see here again limit, the asymptotic value means ultimately everybody will get infected. So susceptibles become 0. And to begin with, there is one person, all these st has become n. So n plus 1, infected persons has become n plus 1. That means there is a town, for example, 100 people are there. One has come from outside. To begin with, susceptibles are 100, infected 1. Ultimately, all these susceptible people, they get infected. So 100 plus 1, ultimately all the persons will be infected. Okay, so simple model. Then I'll present one more model. Then I'll go to the next one. Yeah. You see here, now we are considering here, the removals also. ds by dt is minus beta si, di by dt is beta si minus gamma I, and dr by dt is gamma I. You see, di by dt plus beta si minus gamma I. That means removal we have put. So these people are being removed. This is a negative sign. dr by dt gamma. So here the constant proportion is beta. Here it is gamma. Okay. So there is a parameter which is defined gamma by beta. So and so. S0 is positive. I0 positive. Removes to begin with initial condition is 0. You see how the problem is converted to mathematics. Initial value problem. Okay. This condition. Then this rho gamma beta is called the effective removal rate. The ratio of the rate at which individuals are removed from the infected category to the rate at which they are added to the same category. Okay, this is called effective removal rate, this gamma, right? Then I'll skip all these things, then some asymptotic values, then finally, beautiful conclusion here. S0, initial susceptible value, less than rho. DIDT is initial negative. Epidemic does not build up. Hence, epidemic builds up only if S0 is greater than rho or rho is less than S0. That is only when the effective removal rate is less than the initial number of susceptible. And in this case, all the persons do not get infected. A stage may be reached when all the infected persons are immediately removed. Thus, an epidemic builds up only when the density of susceptibles is high owing to overcrowding and the rate of removal is low due to inadequate isolation facilities. On the other hand, if the isolation conditions are good and density of susceptibles is low, the epidemic fades out. You see, this model was given decades ago. Finally, you see the conclusion. Thus, an epidemic builds up only when the density of susceptibles is high. That is what we are calling social distancing today. That is why when the situation was very critical, the so-called lockdown was imposed so that density can be decreased owing to overcrowding. Rate of removal is low. Why did we impose, government of India impose a lockdown? If lockdown is there, the density is less, infection is less, and meanwhile, you can create isolation facilities. To begin with, suddenly, there were no masks, there were no sanitizers, there were no hospitals, there was no oxygen, there were no ventilator. Government of India needed some time to build up these facilities. So, decreasing the overcrowding, decreasing the density, and rate of removal increase by creating appropriate isolation facilities, we could control it. On the other hand, if the isolation conditions are good and the density of susceptibility is low, the epidemic fades out. You see, whatever we are seeing today, this is being expressed by mathematical finding decades ago. This is a very crude, very simple model. And today the model which is being considered the Sutra model, by 3-4 persons, it gives, of course, they do not simple mathematics, they do numerical simulation. Okay, of course, then you may ask, sir, sometimes the findings are wrong. Yes, It depends upon the mutations. We cannot take all those parameters into consideration. Sometimes the mutations are there, behavior is new. So all those factors can. But this mathematical model gives an idea. It says the peak it can go to is some 4 lakhs, or it will reach the peak in April, or it will die down in July. Accordingly, the government make preparations. The health department makes preparations, creates facilities, temporary hospitals, temporary after the bad experience during second wave because of our lack of preparedness. There was a lot of suffering. Many people died. People who are today, by the grace of God, we are safe. We don't know the difficulty. How many people lost their near ones, dear ones, the kith and kin? How many people struggled because they did not have the livelihood? They have to live and so on. So what I am trying to say is these last 3 sentences, the mathematical study tells us exactly what is being faced today, and this is using a crude model some 40, 50 years ago. The better models give us better things, but of course, always, we should understand there will be limitations for any study, because how does the virus behave? We don't know exactly. The mutations part cannot be taken into consideration in these crude models, right? So based on this experience, this model can be further improved. That is why in some of the phases, the findings of the particular committee, Manindra Agarwal and so on, Krishnamurthy and so on, they were quite close to reality, and that really helped the government in getting prepared for the eventuality, creating facilities and so on, so that we could control in the subsequent phase. First phase, we were very comfortable. Second phase, due to some reason, there was slackness, we suffered. Subsequently, we were more careful. You see, third wave, when Omicron came, many countries, they suffered. But in India, we were very, very comfortable. It is because of some of these studies. Of course, I don't say only mathematicians, engineers helped. The doctors, of course, they play a primary role. The health workers, supporting staff, all those things. What I'm trying to say is mathematics plays a very important role, even in a situation like the epidemiology. Okay, so with this, I close this one. Now I go to the next one, that 1 minute. Yeah, can you see the screen? Hello? Hello?
Yes, sir, it is visible, sir.
Yeah, now I come to what is the time now? 11. I think I will take 1 hour. Is it okay if I take extend beyond 11:30? Is it all right?
You may take however time you want, sir. Whatever.
Okay. Thank you. Yeah, this is a fascinating subject of branch of fluid dynamics, which we call biofluid dynamics. Deals with the fluid mechanical aspects of biological systems. Yeah, fluid mechanics, for a bit about objects and so on. Okay. I think. Yeah. Yeah. See, first let us see fluid dynamics. There are 2 important aims of studies in fluid dynamics. Improved locomotion through fluid media. Enhanced understanding of transport by fluids and circulating systems. You see, people normally study fluid dynamics and publish papers without knowing what are the objectives of these things. Improved locomotion through fluid media. Enhanced understanding of transport by fluid circulating systems. The first one is what we call external fluid dynamics. Second one is called internal fluid dynamics. Okay. Yeah. Research with these aims over many decades as the design of efficient vehicles for locomotion in water or through the air. Okay. That is, you have ships, you have planes, submarines, and so on. Better analysis of circulating systems, transport of heat, various substances, solution or suspension. Okay. The subject of fluid mechanics as well as human civilization. I will briefly run through the historical developments. Notable contributions are from Archimedes, Newton, Bernoulli, Euler, D'Alembert, Lagrange, Laplace, Paisali, Darcy, Navier and Stokes, to name a few. Yeah, this is a classical one. 1904, Prandtl published one of the most important paper giving the concept of boundary layer. In the 20s, I think those who know this boundary layer concept, possibly they would appreciate. A boundary layer is a very, epoch-making paper, a revolutionary paper. 20th century, Karman, G.A. Taylor, Lytle made significant contributions. In the last few decades, CFD, computational fluid dynamics, has revolutionized works in fluid dynamics. There are many branches of fluid dynamics. I will confine myself to biofluid dynamics. Yeah, biofluid dynamics. It refers to the application of principles of fluid dynamics of biological systems. Biofluid dynamics can be considered as a study of human body and its components by the application of principles of fluid mechanics oriented in a sense to medical applications. The fundamental assumption here is world of living and the world of non-living are governed by the same laws of physics. You see here, human body and its components by the applications of principles of fluid mechanics oriented in a sense to medical. Ultimately, it is the medical application which is the main aim of biofluid dynamics. Fundamental assumption is world of living, world of non-living are governed by the same laws of physics. This is the very important assumption. That means you consider the flow of blood in the human body or consider the flow of a similar fluid under similar conditions in the laboratory, they follow the same laws of physics. In other words, human body does not disobey any known laws of physics. That means conservation of mass, conservation of linear momentum, conservation of angular momentum, conservation of energy. All these laws are followed by the human body also. That is the most important things. Yeah, aims and objectives. It is revealed that many analogies exist between human body frame and engineering systems. Both of them function more or less similar mechanical principles. A collaborative study would enable the scientists to understand biological systems better. This understanding in turn would help in the designing of artificial limbs and the diagnosis of diseases. You see, in the beginning I told, by this collaborative study, engineering or mathematics contributes to betterment in the biological system. How? Design of artificial limb. Now we have artificial kidney, which we call dialyzing unit. That is possible only because of biofluid mechanics studies. And we have artificial heart today. We have artificial, today even synthetic blood is being thought of. All artificial, pancreas, liver, and so on. How these things are possible? It is only because of this collaborative study. And in the diagnosis of diseases, if you see, many of the diagnostic techniques, they are getting improved only by biological study. I think, design of artificial limb, I'm sure all of you must be knowing. Abdul Kalam and Somarazu, famous cardiologist in Hyderabad, they together designed one stent. Okay, so that shows how collaborative study between engineers. Kalam is an engineer, Somarazu is a medical scientist, a cardiologist. They together worked and designed one stent which turned out to be quite cheap compared to the stents available earlier. Stent, if it is very costly, people below the poverty line, they cannot afford. So Abdul Kalam collaborated with Somarazu, eminent cardiologist in Hyderabad, and they come out. So that is a typical example of designing for artificial limbs. Diagnosis of diseases. Today, diagnostic techniques are taking, if you compare with 20 years ago, so much of improvement. All this is possible because of the collaboration between engineering and biology. Second one is very important. Nature has provided excellent engineering system living beings, which are far more superior in knowledge than their counterparts mechanical systems. And the better understanding of biological system may help us in sophisticating the existing engineering. This is the contribution of biology to engineering. You see, for example, I was telling about the so-called artificial kidney dialyzing unit. I'm sure many of you know, if somebody's both the kidneys are damaged, then he has to undergo dialysis. He's put on dialysis. What is done there? There is a dialysis unit, which is a very big machine, and then they draw the blood from the body of this person. They pass through this machine. The blood gets purified and then pass it back to the human being. In other words, the dialyzing unit performs the duties of human kidneys. But dialyzing unit, it is a very big unit. But if you take human body, there are two kidneys. I will go much into the detail later. There are two kidneys. Each kidney, the functional unit is called nephron. That's why the nephrologist, we say nephrology, who deals with the kidneys. Nephron is the functional unit of kidney. In each kidney, there are 1 million nephron. That means 10 lakhs. 10 lakhs, second kidney, 10 lakhs. That means 20 lakhs nephrons. In other words, human body, almost 20 lakhs dialyzing units are there. That shows the level of sophistication of human body. If only you can understand these principles, the philosophy, the logic, the structure, the mechanism, the process involved, you can sophisticate the existing engineering systems. You see, mechanical engineering, they study bearing systems. Bearing systems, you have bearing surface and you have a fluid in between which bears a load. If you take human body, we have so many joints. We have hip joint, we have knee joint, we have neck joint, we have wrist joint, we have elbow joint. All these joints are also like bearing systems in the engineering domain. But engineering system, if you take any machine, they give warranty or guarantee only for 3 years, 5 years, 10 years, it gets spoiled. But in human body, if you take these, for example, these joints are, ordinary human being, if you maintain reasonable good health, 60 years he survives without any problem. That means you don't get any knee pain or hip pain or neck pain for 60 years. That means this bearing system works for 60 years. You imagine this with a counterpart in the engineering domain where a machine gets spoiled after 10 years. That shows the level of sophistication of human body. So if you understand human body, you can sophisticate the existing engineering systems. Okay. Origin of biofluid dates back to civilization. I think I'll quickly run through some of these things. Galileo, William Harvey, Descartes, Robert Boyle, Thomas Young, Paisley, Helmholtz, Adolf Fick. I'm sure all of you would have been familiar with these names. Galileo, physicist, but he was also a doctor. William Harvey, who gave the concept of circulation. Descartes, we know. Robert Boyle, Thomas Young, Young's law. Okay, in the LHC we see Young's law. He was a doctor. Paisley flow fluid dynamics people. Helmholtz, Adolf Fick, mass transfer. All these people, they contributed to biofluid dynamics. They were also medical doctors. I think I'll run through. I will not give these details. Only second one I'll give. William Harvey gave the concept of circulation of blood. Every heartbeat ejects 75 ml of blood. 75 into 60 seconds, 60 minutes, 270 liters of blood. Where can all this blood go? Where can it come from? Initially, people had so much of doubts. The principle of measurement led to the discovery of circulation. So then people realized it is getting circulated. He did not exact capillaries. Let us forget about it. Yeah, Robert Boyle, I think some of the important cardiovascular, food mixed in motility in the intestines, air transport to the bronchial tree, flowing renal systems, reproductive system, synovial joint. Some of the systems received attention, not the exhaustive list. External biofluidodynamics, internal biofluidodynamics. External biofluidodynamics is concerned with animal locomotion through the surrounding media. Internal biofluid concerned with heat and mass transfer of fluid flow in animal. However, these two causes biofluidodynamics have one in common, one general character that distinguishes them from the rest of fluid dynamics. The fluid movements are arranged by the working of animals, motile external interfaces, parts of which are highly flexible. Biofluidodynamics. There are two important features of the system which are fascinating and noteworthy. First, the richness of this field from the fluid dynamics point of view, giving the complex organization human body and the systems such as cardiovascular system, respiratory tract, system for transport of lymph and urine. Second, fluid flows in the human body raise problems much different from those raised by engineering fluid flows, and the main reasons are, you see, from fluid mechanics, those who are familiar, unusual range of Reynolds number, unusual multiplicity of tube branchings, unusual distensibility properties of containing metals, unusual fluid properties, unusual pulsatility. Okay, so you see, when you see the human body from the fluid dynamics point of view, it is a very complex problem. It is a very fascinating, it is a very challenging problem, but it needs a deeper understanding of biology and so on. Cardiovascular system. It involves the flow of very complex fluid blood through a very large network of blood vessels, which are of non-uniform cross-section you see here. Flexible, complicated branchings, taperings, sites of curvature, you see geometry point of view. Cross-section is not uniform. It is not rigid, flexible. Branchings are there, taperings are there, curvature are there. That is the geometry of the blood vessels. And our blood, suspension of blood cells, RBC, red blood cells, white blood cells, platelets, medium called plasma. Red blood cells are biconcave discs which translate, rotate, deform, squeeze. You see here, in mechanics, we consider translatory motion. You have rotatory motion here, you have deformation here. It is squeezing through narrow blood vessels. It is highly challenging one. Blood behaves differently in different conditions. It behaves Newtonian for large blood vessels where suspension behavior can be ignored. Behave as a non-Newtonian for small arteries. Pulsatile effect generated by the periodic pumping to the heart. You see, heart is a periodic pumping. It is a pump, periodic pump. So the pulsatile effects are generated. Different non-Newtonian mode of surgery. Casson, Herschel Berkeley, power law, Ribbentrop injection, micropolar. So, for example, I have given some of the models. Bingham plastic, like for example, toothpaste. It has got what is called yield ester. This is known as the constitutive equation. This is the Casson fluid. One is generalization of the other. This is power law fluid. Okay, pseudoplastic, Newtonian, dilatant. Then this is Herschel Berkeley, very versatile model. Particular cases come out to be Bingham plastic, power law in Newtonian. Then this is a Rivlin-Erickson fluid. This is the stress-strain tensorial model. Then polar fluids, power law, micropolar fluid, Casson fluid, and so on. This is the cut. Then mammalian cardiology, I'll quickly run through this. This is that schematic diagram of heart. You see, this is a beautiful one, Where is this actually slide?
Sir, why your voice is not audible, sir? Your voice is not audible, sir. You are in present unmode, sir.
Yeah. Is it okay now?
Okay, sir.
Yeah, you see, the blue blood indicates impure blood, and the red blood is the next animation. Something is wrong. Okay, let me go. Yeah. Now it is coming. Okay. So 1, 2, 3, 4. You see, it is coming inside into the lungs, left part of the heart. Then it is going to the lungs. 2, 3. It is getting purified in the lungs. 4. It is coming back to the heart, left side of the heart, the left ventricle. Then 5th, you see, lower left ventricle. Then 6th, it is going through the various parts of the body. 7, the upper portion of the body. Then 8, inferior vena cava. 9, coming back blue blood to the heart. So 10, 11, 12. Okay, so you see the beauty, right? This is schematic diagram. Imagine yourself in the what you call this particular frame. Right atrium, right ventricle, left atrium, left ventricle. This is a heart, larger artery, large arteries, small arteries, arterioles, capillaries, where the mass transfer takes place, venules, small veins, large veins. Then this is heart and lungs. I think I'll skip these things. I'll explain only cardiac cycle. This is pulse actually. Beautiful one. You see, A stands for atria, V stands for ventricles. Atria first contract. The total, cardiac cycle is about 0.8 seconds approximately. Atria contract, then ventricles contract. All of them, they relax. So when the ventricle contracts only, blood flow comes into the body through what is called aorta. In other words, for about 0.3 seconds, out of a total of 0.8 seconds only, blood is flowing into the human body, right? Then how is the continuity of blood supplied? This is the beauty about simple harmonic motion present in the human body. When blood flows into the aorta, then left ventricle, the valve closes, there is no flow of blood. What happens is, when the blood flows from heart into the aorta, it being elastic in character, it extends and accommodates extra blood. When the valve closes, there is no flow of blood. These valves, being elastic in nature, they try to come back to the position of equilibrium. But because of inertia, they overshoot the position of equilibrium and push blood to the next segment. Next segment get extended and so on. In other words, every segment of the arterial wall executes simple harmonic motion with a frequency equal to that of the heartbeat. And this disturbance travels distally. That's why you can feel the pulse when the blood vessel is closer to the surface, like the radial artery. Doctor, when you go to a doctor, he feels the pulse. He touches the left wrist and try to feel the pulse, right? So this important pulse, which tells everything about the working of the human body. There are doctors who tell all the diseases by feeling the pulse only. Such an important pulse depends upon mathematical concept of simple harmonic motion. Okay, I will skip all these things. Yeah, blood pressure, only thing I will explain, then I'll go to a mathematical model. Yeah, this is blood pressure. I think all of us would have seen this instrument, especially elderly people like me. We go to doctor often to get the blood pressure measured. So the measurement of blood pressure simply depends upon mathematical, fluid mechanical concept only. You see here blood flow is, first figure you see, first diagram, blood is flowing. Then he wraps that particular sphygmomanometer, that cloth, around the brachial artery. Then with the help of this, this gauge, he tries to inflate this one. When the pressure in this, for example, this one, it is more than the maximum pressure in the blood vessel, then it presses the blood vessel, there is no flow. Then the doctor puts a stethoscope here and slowly releases the gauge. When the pressure here slowly starts decreasing, when it just falls below the maximum pressure, then blood gushes out. At that time, he hears a thud sound. That is for normal blood pressure, 120. Then slowly, he keeps releasing and the character of sound changes. Then he measures the diastolic blood pressure. So systolic blood pressure, diastolic blood pressure measurement simply depends upon fluid mechanical considerations only. Yeah, I think I'll skip all these things. The beautiful pictures are there, but it's not necessary. Yeah. This one I will explain and I will go to the mathematical model. You see, when we go to a doctor, doctor measures the blood pressure in the brachial artery, upper portion of the arm. Why it is so? You see, suppose you take a tub, some fluid or water is there. What is the pressure at the surface of the water? It is atmospheric pressure. If you go down, then there is force of buoyancy. You see here, this PA is there. Then you have rho GH. Okay, depth, as the depth increases, the pressure increases. That's why if you go down, there will be opposing force. Then, suppose you give a thrust to that particular surface, some excess pressure comes. So this excess pressure is generated. So the pressure in the tub contains this atmospheric pressure, force of buoyancy, excess pressure. Now, doctor will be interested not in the atmospheric pressure, not in the rho GH component, only in the excess pressure generated by the periodic pumping at the heart. Now, you see here, what the doctor measures is transmural pressure, the difference between the internal pressure and the external pressure. So it is P naught PA. So this PA disappears. Then this brachial artery, where the blood pressure is measured, it is at the level of heart. At the level of heart, H is 0. Therefore, this component disappears. Only he gets PA component. That is the reason why blood pressure is measured in the brachial artery. So all these things clearly show how fluid mechanics is important in this particular situation. So I think I'll skip these things. Wave propagation, I'll skip these things. Then you see, yeah, this is a beautiful this thing. Reflection, transmission of waves at junctions. I will not spend much time on this. This you see, human body, the blood vessels, they branch. So this is the incident wave. Incident wave transmitted. There are two daughter tubes are there. Transmitted, one transmitted to a part of the wave is reflected. So incident pressure, transmitted pressure, reflected pressure. So you see, these are the conservation principle. P incident plus P reflected is equal to PT1, PT2. Similarly, with respect to flux, flow rate, characteristic impedance is a very important parameter. In electrical circuits also, they say impedance, that is resistance to the circuit. Similarly, resistance to the blood flow. Whether you see electrical engineering, circuit theory, or blood flow in human body, they follow the same sort of principles. Then PR, mathematical analysis ultimately give important reflect and transmit waves of same shape. Some of these results, you know, this is, I give only the final results. This is the very complicated subject. Reflection, transmission, incident wave, transmitted wave, and so on. Okay. So now I will go to the nephrons, kidney problem. Quickly, I'll run through it. I don't know what is the time. 11:30. I'll take half an hour. Kidneys are one of the excretory organs in human body, like skin and lungs. Two major functions of kidneys are they excrete most of the end products of body metabolism. They control concentrations of most of the constant body fluids. See the schematic diagram. You see here, for example, this is known as Bowman's capsule. The arteriole comes here, afferent arteriole. It forms a tuft of capillaries known as the glomerulus. Then here filtration takes place. Then it goes out the afferent arteriole. The filtrate, you know, as I told in the beginning, human body does not disobey any known laws of physics. The filtration takes place according to the principles of osmosis or diffusion only. Because we don't want impurities to be present in the body, they don't go out. They go out only because of known principles of physics, known laws of engineering only. Then when it gets filtered, it contains a lot of constituents which are needed for the human body. That is the beauty of human body. Then as it passes through these tubules, you know, this is called proximal convoluted tubule. This is called loop of Henle. This is called distal convoluted tubule. This is what is called collecting duct. As it passes through these ducts, constituents which are needed for the human body, they get reabsorbed back into the blood. Again, the walls are so designed, so structured that as it passes through, those quantities get reabsorbed back into the blood vessels, right? So the filtration takes place in the reabsorption takes place in this particular proximal pulmonary tubule. Yeah, this is a flow, Bowman's capsule, efferent arteriole, beautiful figures. Then basic function nephron. Each kidney contains more than 1 million nephrons, each works independent of the others. Anatomy of nephron. Already I have explained these things. I will skip. Physiology of nephron. Filtration, reabsorption, secretion. Phlomeral, yeah. Filter pressure. Favorable pressure, 50 millimeters of mercury. Opposite hydrotic 10 millimeters of mercury. Colloid hospital 30 meters. Appeasing was 40. Favorable is 50, 10. So you see here, when we consider the fluid mechanical considerations compared with the reality situation in a kidney, they always match. Net filtration, mechanism of urine formation. Yeah, you see, human being, total quantity of glomerular filtrate from both the kidneys, average is about 180 liters per day. And its weight is more than 2 times the total weight of the body. Average person excretes approximately 1.5 liters of urine. 99% of the glomerular filter is reabsorbed back into the peritubular capillaries. So this reabsorption has received a lot of attention in the literature. And I'll quickly run through this. Yeah, this is one problem which we have done, myself and Professor Piyush Chandra of IIT Kanpur and Dr. Yamal Kaimal from Trivandrum. We did this problem. This was long ago, of course. It was published in a very good journal. And I will tell you about that later. Yeah. So a fluid mechanical study. Oh, sorry. This is the boundary you see here. Ax equal to A0 into Rx. 1 plus epsilon e power beta x minus 1. Beta less than or equal to 0. Minus less than. Why this particular equation is taken? We have gone through Gray's anatomy book and AC go to the physiology book. Then we have taken the dimension from the what you call the dimension for a particular case study. Then we try to fit using curve fitting. We try to fit this equation. Ultimately, it was matching. Okay. So that is how this particular equation was chosen for the boundary. Then, of course, it is the Rayleigh flow is very low. So inertial effects are neglected. First two equations are the linear momentum equation. Last equation is continuity equation, conservation of mass, conservation of linear momentum. Yeah, this is the beautiful this thing. Tangential velocity at the wall is 0. U plus dA by dx into V. dA by dx means it is tan theta slope. Sin theta by cos theta. That means U cos theta plus V sin theta equal to 0 at the boundary. It is because of the what you call non-uniform cross section. Then as the filtrate flows through the tubules, it gets reabsorbed, so the flux decreases. It is an exponential decrease. Regularity conditions. We have into the steam function, non-dimensionalization, ultimately then it is reduced to a biharmonic equation. These are the boundary conditions. Yeah, here one problem comes when we try to do asymptotic solution. This contains the perturbation parameter, but boundary there is a perturbation parameter. How to get rid of that? So we have used the Taylor series. Taylor series we teach in the first year of BTech in differential calculus. That Taylor series came to our rescue in getting over this difficulty. You see, at this point, then using this, we got over that. So 0th order, first order, stream function, so and so. Then mean pressure across the cross section, right? Then mean pressure drop. This is the important characteristic here, right? Then of course, mean pressure drop. This is the shear stress. Then we have taken data from rat's kidney, which was available in the literature. This is the flux. This is the radius. This is the viscosity, length of the tube, pressure drop. Then, yeah, this I'll give. Yeah, this is the table, mean pressure drop. In fact, now let me tell you, when we published this paper long ago, those days, there was no internet, was not very common. So we used to send, people used to ask us, please send your paper. We used to, please send the reprint. Reprint they used to ask those days. So when we published this paper, we got requests from all over the world. Let me repeat, all over the world, from many types of doctors, physicians, cardiologists, radiologists, nephrologists, urologists, and so on, from different countries. What they mentioned is, we are amazed at the potentiality of mathematics, and in particular fluid dynamics, in understanding the processes and phenomenon in the renal system. Please send us a reprint. I'm telling these things not to boast about myself or my colleague, but I'm telling these things to emphasize the potentiality, utility, applicability of mathematics, in particular fluid mechanics, in the context of biological systems. In fact, I still have those, reprint requests, nearly more than 100 reprint requests those days, long ago. Yeah, some of the peristalsis, I think I'll take another 5 minutes. Peristalsis, I will skip, I think. Yeah, this is the beautiful, these things, some of the diagrams. I think this I will skip. Peristalsis is another area which is which contains two important phenomena. One is called reflux, other one is called trapping. Okay, stenosis. This is refers to the unnatural, abnormal growth. Okay, which ultimately is a heart attack. Current normal circulation. You see, this is how plaque develops. People get heart attack. So if it develops in the coronary artery, it results in a heart attack. If it happens in the blood vessel which supplies blood to the brain, it results in the paralytic stroke. You follow? Whether it is paralysis or heart attack, ultimately, mathematical model is same. One more thing I want to tell is, oil industry, many times in the oil industry, in the pipes which supply oil, there will be blockages or any other fluid, more so in the case of oil. So whether you consider blockages in oil pipes in oil industry, either whether you consider heart attack, whether you consider paralytic stroke in human body, the mathematical model or fluid mechanical study is the same. That is the beauty of mathematics. Mathematics unifies all branches. You follow? Whether you take a wave equation, whether it is vibration of a string, whether it is vibration, whether sound wave, light wave, pulse in human body, it is a wave equation studies. Parameters may vary, complexity may vary, concept is the same. That is the beauty, fascination, unifying nature of mathematics. Okay, so you see here, dead muscle. In this case, the person gets angina, pain in the heart. Human body gives lots of, what you call signals. And I'll skip these things. Yeah, spermatozoa transport. This is a very interesting one. Swimming motion of spermatozoa in human reproductive system has risen considerably in the last 6 to 7 decades. Tyler, Shack and Lardner. We also did some work. Shack and Lardner consider two-dimensional model consisting of a doubly infinite sheet swimming between rigid walls, assuming that the wavelength of most of the swimming sheet is large compared to the channel spacing. So we consider, you see here, usual equation, pressure term, viscous term, initial term is ignored because spermatozoa transport Reynolds number is very low. This is the continuity equation. Then this is the equation of the sheet. Spermatozoa is modeled as a sheet. This is the boundary condition. Yeah, this is the additional condition. This is a very complicated problem actually. The sheet is self-propelling. Spermatozoa, when after it is introduced in the female reproductive system, it travels to the site of fertilization in the fallopian tube on its own, facilitated by peristaltic waves which move on the walls of the fallopian tube. So you see here, it is self-propelling. This is the force acting on the upper side. This is the force acting on the lower side. these two balance out. This is an additional equation, force balancing condition, which needs to be considered when you study the so-called spermatozoa transport. This is a very complicated one. In fact, we published one paper in Journal of Biomechanics long ago. So you see here, in addition to the conservation equation, in addition to continuity equation, the equation of the sheet, boundary conditions, peristaltic transport, this force balance equation, force balance condition makes the problem very complicated. Okay, then there are things. Okay, so I think I will stop here the lecture. But before I close, I want to tell a few things. One thing is, people who want to work in biofluid-dynamics, it is a very challenging area. People do a lot of work, people publish lots of papers, but they don't understand. That is very unfortunate, because here the geometry, as I already explained, geometry is very complicated. The fluid is very complicated. Networks are there, the branches are there, taperings are there, curvature sites are there. Fluid is non-Newtonian. There are suspensions, they deform, they squeeze through. Name any complexity, it is there in human body. In order to understand that, you need to have good comprehension of the concepts of fluid mechanics. Then you need to know something about the physiology, anatomy, working of those systems, and you need to have good command over mathematical techniques, right? Like especially numerical technique these days. Then only you can do some meaningful problem. What I have presented is only a glimpse. I could only scratch the surface of this fascinating branch of fluid dynamics. But if you dig in deep, you will be able to find many more fascinating, challenging, interesting things about the human body. Okay? You see, as I always say, nature is our greatest teacher. You follow? We tried to study most of bat in darkness. We came up with radar. We tried to study, Joseph Monier was working in a garden. He came across a plant with roots on the ground. Then he came up with RCC, reinforced concrete. Today, all the buildings we use reinforced concrete. It is by nature. Similarly, by studying, for example, underwater organs, we could get submarines, aeroplanes, satellites, rockets, everything. It is only by imitating nature. Similarly, by understanding more about human body, using more complicated models, we may get better comprehension about the working of the human body. That's why now there is a lot of collaboration between engineering departments, technology, mathematics, and medical. IITs are starting medical schools. ISC Bangalore, they are going to give, after MBBS, they are going to give a MTech dual degree. So you will be admitted to MBBS. You will be exposed to the technological concepts. You will have MBBS degree, you have a technology. Because the reason is, if you work in isolation, what you can achieve is less. Okay? Let me stop sharing. Yeah. If you work in isolation, what you can achieve is less. But if you involve in collaborative study, this would lead to phenomenal results. Okay, maybe you will understand much better. Biology may contribute to engineering, engineering may contribute to biology. Okay, so please, those of you, my attempting this lecture is to illustrate the importance of mathematics, potentiality of mathematics, applicability of mathematics, some case studies, and then in particular fluid mechanics. Fluid mechanics is a very fascinating branch, but today fluid mechanics is losing all its importance. Why? Because people are not doing serious work. When I joined for my PhD work way back in 1975 at IIT Kharagpur, fluid mechanics was the most sought after subject. But today it is not the case. Many of the IITs, they are removing fluid mechanics from the core structure. They are putting only selective, because people think fluid mechanics people are not doing serious work. So my sincere appeal to all those young faculty members is, if you want to work in fluid mechanics, try to study the concepts of fluid mechanics, the fluid physiological aspects, the techniques, then try to do more meaningful work, and you will be able to do wonderful service to the branch of fluid dynamics. And finally, normally I give this verse, there is a small stanza. When we go to temples, towards the end of the puja, the priest recites what is called mantra pushpam. Sahasrasirusham devam vispaksham visasambhavam. At one stage he says, Padmakosa pratikasakam hrudayancha adomukam ado nishyavitas yante nabhyamupari tishtati. What does that mean? Padmakosa pratikasakam hrudayancha adomukam. What is that? Heart is like a lotus flower. Adomukam, it is like face downwards. If you say heart, it is like face downwards. Ado nishyavitas yante nabhyamupari tishtati. What is this? Is called Nisti in Sanskrit, This is called Nisti in Sanskrit. Ado nishya, it is below that. Vitasya ante, this is called Vitasta. So if you put one Vitasta from this Nisti, the heart is there. And Nabhyam uparitistati means it is above the navel. So somebody could think of the shape of the heart and its location in the chest region thousands of years ago. That speaks volumes about the knowledge and wisdom of our ancient people. Unfortunately, those things were not documented, those things were not patented, and so the Europeans, the Western people, got credit for all these discoveries and inventions. Okay, thank you so much for your patient hearing. Even if some of you get inspired by the concepts of mathematics and the concepts of fluid dynamics, my effort would be worth undertaking. Thank you so much. Yes.
Thank you, sir.
So there is a question in chat box.
Yeah.
Are principles of fluid dynamics such as Bernoulli's theorem applied to blood flow in human body?
I'm not seeing the message. Can you please read the message?
Are principles of fluid dynamics such as Bernoulli's theorem?
Yeah. Bernoulli's equation?
Bernoulli's theorem applied to blood flow in human body.
Yeah, it does. I told you now, all known laws of physics, all known laws of fluid mechanics invariably apply. You follow? Human body does not disobey any known laws of fluid mechanics, known laws of physics. Yes. Any other question?
If someone met an accident and if the nose is damaged, to replace it, which mathematical model is used?
Please repeat. If somebody meets with an accident,
if the nose is damaged,
nose
is damaged, to replace it, which mathematical model is used?
There, to the best of my knowledge, the plastic surgery nose replacement, possibly models are not considered. I don't know. I am not aware of any model. For example, heart, pancreas, spleen, kidney, these mathematical models are considered. There, it doesn't come strictly under fluid mechanics. It comes under solid mechanics, elasticity, because this is a structure, This is the structure. The structure, when you want to put it, but you can always imitate it. You can imitate it. You can simulate it. So it needs collaboration between medical scientists and structural engineers in order to consider what is called an artificial nose. You follow? So, of course, there, because there is a fluid also, air is also flowing to that. It needs a collaborative work between fluid mechanics people, solid mechanics people, and doctors. Then you can consider mathematical model.
Okay, sir. Please explain formation of differential equations in deflection of beams.
In deflection of beams?
Yes, sir.
Deflection of beams. Yeah. See, I think we study in BTech also now. When there is a deflection, for example, we take damping, vibration, all those things. Differential equations, I think engineering books, engineering mathematics, they give all these things. Or if you want, you can refer to Sokolnikov's book. It gives all these details.
Okay.
Yes.
That's all, sir. Sir, thanks for explaining the beauty of mathematics, sir, by telling the importance of differential equations and curvatures and other examples, sir. You also explain a real life applications like corona by telling how to form mathematical modeling in corona situation by using deterministic models wonderfully, sir. And you explained about the blood flow in heart, expression of blood pressure amazingly, sir. And మీ సాంస్క్రిట్ పద్యాలు కూడా మాకు చాలా బాగా నచ్చాయి సార్, చాలా బాగా ఎక్స్ప్లెయిన్ చేశారు సార్. And it's time for vote of thanks. On behalf of Gates Institute of Technology and Department of HNVS, I extend a heartfelt thanks to Professor Radhakrishnamacharya sir for an amazing session and sharing a vast knowledge on mathematical modeling, fluid mechanical aspects of biological system. My hearty thanks to management, faculty for their constant support and guidance to organize the event. My sincere thanks to the technical team for supporting in smooth functioning of the session. My special thanks to the participants for their participation and cooperation in making this session a grand success. Thank you one and all. Thank you, sir.
Just one small clarification.
Yes, sir.
You see that epidemiology model, I have not done that work. I have taken from literature, I have presented it. But that renal flow problem, that of course we did that problem. Some of the other things I've taken from literature. I have presented them in a sequential manner. So epidemiology model, I have not done any work on that one, but I have taken that model because it is relevant to the present context and that shows the potentiality of mathematics even in a context like COVID pandemic. That is the reason why I presented. It is not my contribution. Okay, clarification.
Thank you, sir. Thank you so much.
So can I leave now?
Yes, sir. Thank you, sir.
How many people attended the lecture? Can you get the data?
150 members, sir.
How many people?
150 people, sir.
Okay, right. Thank you. Can I leave now?
Yes, okay, sir.